All right, let's rock and roll. Cool. Hey, everyone. I was going to start with, did you miss me? But I actually don't want to hear if you didn't, so I'd rather just not know. Let me make sure I'm following the stream here. We're all good. Hello. Why is technology so terrible? Okay. There we go. Yay. Okay, thank you. Okay, so if you take a moment. Okay, thank you. Oh, it's like, who's talking? That's good. Okay, so don't need that. Okay. So if you take a moment and reflect a little bit on where you are in the course, think about all the things that you've done. It's actually kind of crazy. Maybe you didn't think you could fit all that into blah, blah, blah weeks. Anybody know what week it is? 10? 9? I think it's roughly 9. There's like 6 more weeks. So you've learned assembly, you've written a web server in assembly, you've reverse engineered binaries, cracked password or cracked keygen checkers. You've performed networking attacks. Now we're going to learn about the stuff that tries to defend against a lot of that. So we're going to look at crypto or cryptography. The first question, or the first, I guess, statement, just in case you are curious, we will not be talking about Bitcoin or Ethereum or any of your favorite like cryptocurrency scams. We're not going to touch any of that stuff, okay? Good? There are lots of good resources to learn about those things. That is not what we are interested in this class. We are interested in the old real definition of cryptography. So what is that? What does that mean? Getting rich? I think that's not true. Unless you maybe become a cryptographer that works for the NSA, then you can have a good life. I don't know if they're becoming like super rich, but. So what's cryptography? Hiding data. Keeping things secret, keeping things safe. Is that something you care about? Yes, because you're sitting in a classroom or online watching somebody talk about this in a class that you're required to take. So you have to care about it somewhat. So if you break it down, I don't speak, if anybody speaks Greek, it comes from hidden or secret writing. So this is kind of actually the groundwork of cryptography. And it's really, actually, and this is the really interesting thing that we'll learn is this is only one aspect of cryptography, is this notion of keeping something secret or hidden. There's other properties that we actually want to enforce with cryptographic and cryptography, cryptographic primitives, or with cryptography. And so we'll see that as we go along. But let's first define some terms and terminology. This is very helpful, like what I mentioned of what we're not going to be talking about, right? That's part of defining terminology of what cryptography is. So we're going to talk about encryption. So if you were to, using what you know or heard already, what is encryption? Seems like this fancy word they use on a TV show of like, oh no, it's encrypted. Yeah, maybe manipulating data in such a way that I can make a great cryptographic encryption algorithm. You give me any data you want, I'll give you back a bunch of zeros, and now you can no longer read that data. Is that a good encryption mechanism? What?
It's only good one way.
Yeah, it's only really good one way, and then it's kind of useful because you can't ever go back, right? So the key idea, the notion that we're trying to do is with encryption of transforming a message, and message here can be very, very broad, transforming it so that the meaning is concealed, so that way if I encrypt something and I send it to every one of you in this class, none of you will actually know what that message means and what I'm trying to say. And again, what I was trying to get at, the only reason encryption is useful is if you can decrypt something. So that is to reverse it. If you just gave me something and I gave you back zeros for everything you give me, that's not an encryption function because you can't decrypt it. If you gave me those zeros back and was like, yo, I want this original message, I'd say, hey, haha, I don't know. I encrypted it. I don't know how to decrypt that. So that's a key aspect here. So this is like, again, defining terms, right? Encryption, you can think of it as as we'll get to, we'll look at, usually what we talk about is plain text. So plain text meaning the message that exists in a language that we can understand and read. We transform that through some encryption process and we get ciphertext. So the ciphertext, so it should be the case that, as we'll see, nobody else can derive what the plain text is from that ciphertext. We'll see various cases where this is true or not true. And in your assignment, you will be actually breaking these crypto systems and demonstrating that you can extract meaning. Which brings us to our next thing. A crypto system, so this is just the definition. So when I say that, I mean a specific type of cryptography, and we'll talk about these specific things of exactly what that means. We'll start all the way from very, very basic ciphers that you can do in a crypto system that you can do with just pen and paper very easily, to what is in modern day cryptography and cryptographic systems. Oh, great. Plain text, the original message, ciphertext. So you can think of, and you should think of, encryption as a function. So it takes in plain text, and what does it output? Ciphertext. And what about decryption? It takes in what? Ciphertext and outputs plain text. Yeah, this is a way to conceptualize and remember these concepts and these things. Okay, a cryptographer is probably not you. It's also not me. I'll be very straightforward up here. Maybe should have told this at the start, but that's fine. I am not a cryptographer. Cryptography is, well, I don't know if that's my least favorite part of security, but I don't know if any of you are super mathematical people. If you are, I think that's excellent, and you will hopefully get the underlying knowledge behind these cryptography schemes. I definitely do not have enough math intuition and knowledge, but I know what crypto systems are. I know how to use them. I know what they do. I know how to attack them. Even I can do that, which means you can do that. So you will, and I'll harp on this, you will probably, so cryptographers usually invent new encryption algorithms. There's all kinds of crazy stuff and schemes that are even now being introduced. On the flip side, people that break cryptographic systems are called cryptanalysts. And these are either break the algorithms, which means they break kind of fundamentally how it's done, or they break the implementation. Questions on this? So you will be, right now, you're playing the role of the student cryptographer, understanding how these algorithms work. And on the assignment, you'll be playing the role of the cryptanalyst, breaking these things. All right, so we talked about this a little bit. In terms of the security properties that we've talked about, what can cryptography give you? So we talked about concealing meaning, right? What of the three super important, I said you should never forget this, security properties, does that enforce? And you remember the acronym for those three at least? CIA. So which one of those does that? Confidentiality, exactly. So, and this actually, like, I mean, this should kind of blow your mind that we can use math for this stuff. Like, we'll get into, I think probably on Monday, we'll get into public key crypto with integer exponentiation and all this insanity that, like, as they were discovering this math, they thought they were doing pure mathematics, and it turns out it has an application that's used every day by you when you go on the internet. It's wild that these parts of math allow us to do this. But confidentiality is not the only thing we may want. We may want integrity. So we talked about integrity, CIA triad. What may, or what things, like, how could cryptography help you with something, verifying the integrity of something? Or why would that be useful, let's say?
Make sure only authorized people can edit the...
Making sure only authorized people can edit? I would say, we'll get into that, I think, next. We'll talk about access control. That decides who does what. But maybe we'd want to know if somebody tampered with it. Have you guys ever seen, like, a spy movie or something where they'll put, like, a hair on the door, like, right on the door? so that way, if the door is opened, the hair will fly away, and they can check if that hair was there. That means nobody has entered that door. Have you seen this at all, or am I just making stuff up and you're just nodding along? Yeah, it seems plausible. Somebody could have done this once. Yeah. Anyways, that would be something to a measure to try to ensure integrity. As we'll see, there's other ways where I can send a message to this whole class, and you can all verify that it was exactly the message I intended to send. And Connor or JJ weren't spoofing me and actually changing the content of that message. We'll see later about authentication of how we can use cryptography to authenticate. Hey, who are you? What kind of, actually we'll see it in this module. And finally, the property, this is a little unintuitive, but non-repudiation. I think we talked about that briefly when we talked about the security properties, but this is the notion that if I tell, I don't want to use, I'll use the stock analogy. So if I tell my stockbroker, hey, I want you to sell 100 shares of Apple, and the Apple prices go up, like Apple share prices go up, and I say to them, whoa, why'd you sell all my stocks? That wasn't me that sent that. That was somebody else, right? So this would be a way that I could send a message to you all, and you know that it was from me, and I couldn't say that it was actually from somebody else. Cool. Okay. So there's a lot of math in cryptography in general and crypto systems specifically. But this stuff is very easy. This is just used in order to conceptualize and understand what are the different pieces here involved. So you see fancy mathy letterings, I guess font would be the right word here, of these quintuples and E, D, M, K, C. If you're not a math person, don't freak out. It's okay. This stuff is just take it thing by thing of what are these things, what are they trying to say? You know about sets? Yes, sets, just groupings of things. That's all these are. So M here is a set of plain text. So some crypto system has a set of plain texts, a set of keys, a set of ciphertexts, a set of encryption functions. So usually we'll talk about encryption function as one thing, but you can consider different types of encryption functions. What's this notation here? When I say a set of encryption functions E such that MXK arrow C, what does that mean?
Matrix.
Yeah. It's a function, and so it's a function, and what does it mean? So the arrow basically means function, and so how do you interpret the rest? N cross K. Essentially, I treat this as a programming function because I say, I don't want to think about math, I want to think about programming because that's what I like. And so this is a function E that takes in two parameters, one from M, a plain text, one from K, a key, and outputs something from C, a ciphertext. And if you think about it at that level, this is telling you the type of that function, literally like you're used to thinking about types. This is a function E, takes two, returns one, and you know the types of each of those things, a plain text, a key, and a ciphertext. Pretty cool, right? This actually matches similar to what we talked about as an encryption function being a black box that you shove in plain text and you get out ciphertext. But what was missing there was this notion of a key. And we'll understand what that means in a second. So D is going to be the reverse of this, where is a set of decryption functions with the type signature of a ciphertext and a key, and returns and outputs a plain text. Easy? All right, that's it. Is that it? Did we do all of them? Five? Yeah. So simple. There's just a formal way of defining. If somebody says, hey, I have a brand new crypto system, you don't have to say, what does that mean? You can say, okay, great. Show me these things. Has any of you, I said you're learning to be cryptographers. Have any of you played the role of a cryptographer before? Have you invented a cryptography or a crypto system? None of you? Yeah?
I mean, I implemented RSA.
Okay, that's too advanced. I'm talking like when you were younger. Like I invented, me and my friends invented something incredibly stupid to write letters to each other. Where I think it was, you'd write like a paragraph or words, and the first letter of each word was the actual message that you wanted to send. And No, I'm the only one who's done that. Oh, you guys all had phones growing up, huh? Yeah. 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 See, it's like people. See, okay, Pig Latin is a good example, right? We're doing a tweak on Pig Latin. I definitely can't do Pig Latin, but my neighbors could, and it drove me crazy because I had no idea what they were saying. So yeah. Anyways, these are things that you can do. Yeah.
You have friends that encrypted just do.
I guess I did. Yeah. You need. I guess that's step one: get friends as a kid, and then send messages to each other. Crazy is that this notion of cryptography and wanting to keep secrets has existed for a long time. Why is this so important? So in what context, let's say before computers, is keeping secrets or being able to pass secret messages not to your friends or I guess imaginary friends? You can always write a letter to your imaginary friend. Why would that be useful? Okay, you have thoughts? Louder. Yeah, so a military context, right? So you're a general, and you need to tell your whatever is under a general, your captains, that like, okay, we're going to attack at dawn. I think that's actually an example, not here, but in other stuff. And so you send out messengers with that message. If they get intercepted by the enemy, now they know your plans, right? And you may or may not know, depending on that communication mechanism, if that message was intercepted. But if it's encrypted in a way that they can't read it, like, should you just assume that they can't read it because you speak a different language than them? Why not? Yeah, they could have translators. Like, that would be the very first thing. If you're fighting someone, find people, hire them that know that language. Yeah.
People just like privacy.
Yeah, or privacy. I think was it Da Vinci I'm thinking of, who took notes in his notebook with his left hand and backwards? So that as a form of encryption, so that other people couldn't read and steal his notes, but he could read it later. Does that get just undone by a mirror? Yeah, not the greatest encryption scheme, but maybe it's like you have to, I guess having a mirror would be a sign of wealth then. Anyways, getting off topic. So crazy is that this description of crypto systems, so this is, again, kind of insane that like nowadays what is literally the reason why you on your laptop today can talk securely to your bank and transfer money between people is because of ideas that were alive back then. So this is, I think this is 56 AD. So this was about the life of Julius Caesar. If he had anything confidential to say, he wrote it in a cipher, that is, by so changing the order of the letters of the alphabet that not a word could be made out. If anyone wishes to decipher these and get to their meaning, he must substitute the fourth letter of the alphabet, namely D, for A, and so on with the others. So this is a very simple Caesar cipher. I mean, this is literally named after Julius Caesar. We call it a Caesar cipher. The idea is you shift each of the letters of the alphabet, in this case, forward 4. So if you had an A in your plain text, you would substitute a D in the cipher text. If you had a B, you'd have E, and this alphabet is hard, so I'm not going to do all of them. But you would do that for each of them. What happens at the end? What do you do with Z? You just say, no Z's, no Y's, because it's gone off the edge of the earth, it's fallen. Wraps around to the front. So you'd go down to the front, so Z would go 4, so it'd be A, B, C, right? Pretty cool stuff. And something you could do, I mean, obviously they did it without computers because they literally were doing this in 56 AD. It's 56 BC. I don't know. So we can describe, using our formalism of a crypto system, this Caesar cipher. We can say that M is a sequences of letters, so that's the plain text messages. K is the keys are I, such that I is some integer between 0 and 25. Why is it 0 and 25? Why? Yeah, because there's 26 letters, so this is how much we're shifting. Is 0 a good key to use in this crypto system? Why not? Yeah, because then your ciphertext is literally exactly the same as your input, your plain text. Cool. So your encryption algorithm is, take all the letters from the message and do M plus K. So increase, right? M plus K. So take whatever the integer 0 through 26, or 0 through 25 of the alphabet, add K to it, mod 26. What does mod take care of? The wraparound. So we don't have to worry about the wraparound. That's what mod is great for. And how do we decrypt? Yeah. Not break it. How do we decrypt it? If we decrypt, we know the key. We know the key K, and we have a ciphertext message C. Say again? Subtract K. Exactly. Same algorithm. Or you can do 26 plus C minus K, because this is more confusing, I guess, but your way is much better. So yeah, take the ciphertext, subtract K, so essentially move backwards. So if you knew the key was 4, and you got a D in the ciphertext, you would go C, B, D, A, 4 back. So I know that's A in the plaintext, and that's how you could decrypt the message. And the language, the set of plaintext characters is the same as the set of C characters. Cool. So is this the perfect crypto system? Did cryptography never evolve since then? And we're all just using complicated Caesar ciphers? Why not? Yeah, so brute force to break it. So if you were going to break it, now, if you imagine, what is the cryptanalyst job? The idea would be you get a ciphertext C, you do not know the key K, so can you follow this decryption algorithm D? No, because you don't know K. Now, if you were to break this, what would you do? So somebody said brute force. What does that mean? Yeah, so try every number from 0 to 25 of the shifts. You probably don't need to try 0, but that doesn't matter for this. You do the shift. You write out what that resulting message is, and how do you know when you've got the message? Yeah, when it looks like a word or sounds like a word. Yeah, it looks like it could be in the language that you care about, like English. Cool. Yeah. So we talked about the adversary. So now you're playing the role of the adversary, the attacker. Why do we want to pretend to be attackers and break these systems? Isn't that mean and bad? You should just be a nice person and not break anything. To test them? Why do we care about testing them? I created them. I know it's great. Caesar created this. He's great. Yeah, so one way would be, do we know they work? If we can't break it, do we know that they work? Yeah, maybe not. If we can break it in this class, we know it's bad, right? But if we can prove that it's broken, then we can demonstrate that we shouldn't use it. For the crypto systems we're talking about now, we assume the adversary doesn't know the key. Is this a realistic assumption? Why shouldn't we assume that they don't know what algorithm we're using? Maybe with the code, we can reverse engineer it, which is actually why we looked at reverse engineering. There's a lot of what in the past, I don't know about this year's, the NSA Codebreaker Challenge. A previous one was some kind of software that did a one-time passcode that changed every second that you had to reverse engineer and extract, and that was like a crypto thing that you were breaking. So yeah, we can extract it from the implementation. Yeah. Sometimes you can make a guess. You can maybe guess what it is. But again, what's our goal? Why are we trying to break this stuff? Yeah, to either show that it can be broken and we shouldn't use it, right? If the if the U.S. government was saying, "Hey, don't worry, we've encrypted all of your secrets with a great Caesar cipher," you should say, "Whoa, whoa, whoa! No, thank you. I would like a real cryptographic algorithm that has been verified by mathematicians and cryptographers, and something that's withstood cryptanalysis by attacks." Because you could say, I could break that. That's not encryption. It's the scheme is fundamentally broken. And so the assumption here, there's a kind of underlying notion that I'm trying to get at of this concept that people bring up of security through obscurity. So that's like that crypto system that I told you about hiding the messages in the first letter of each word. If you don't know what that's the crypto system and I write plausible looking text, you may never actually identify it. That doesn't mean it's a secure system, right? So the notion should be that like if you want to convince somebody that your system is secure, you can't say, but I'm not going to tell you how it works. Like the whole security of a crypto system must depend on this key and the underlying algorithm. Not the fact that like, hey, they don't know the algorithm, so therefore it's secure. Because if you can break it with the algorithm, then it's definitely broken. Does that make sense? Cool. Okay. But as an adversary, even if we may have this notion of, okay, we know the algorithm but not the key, we ourselves may have different capabilities that we can do. One of the things is the scenario we just said. We're on the opposing side of Caesar. Our forces have captured one of his messengers, and now we have a ciphertext. Just the ciphertext. We'll talk about in a second. Just want to double check that we'll talk about how to break this, even with just the ciphertext. So this is like the lowest level of capabilities that you can have, but you can actually intentionally give your adversaries additional capabilities. You may give them the ability to encrypt whatever they want, like a known plaintext attack. So a known plaintext attack is, I ask the crypto system or somebody who's running this, hey, I have this message M, encrypt it for me. So you don't see the key, they encrypt it for you, and then you get the ciphertext. So if somebody was offering this for a Caesar cipher and you had a known plaintext attack, how would you try to figure out the key? Yeah. You don't have ciphertext yet. You have to tell me what to encrypt. So I'm Caesar. I have a key in mind. You tell me what you want me to encrypt, I will give you the ciphertext. Yeah. Yeah, so you give me A, I give you T. What does that tell you? The key is whatever that difference is. I just made that up in my head. Let's say D, because we already did that. That's 4. So I give you back D. Now can you tell me the key? Yeah, the key's 4, right? Correct. So they know. In this case, we assume the adversary knows and that they don't know the key. Their goal is to get the key, but they have the ability, not that they've stolen a ciphertext, but they can get me to encrypt anything. So it's actually how a lot of, every time, as we'll see, you talk to a web server, it encrypts stuff. You may or may not know exactly how it does it. Or I guess the other good example here is often websites, when they store like cookies on your browser and they want to make sure you haven't modified those, they will do some encryption on there and store some encrypted stuff. So you actually have some control over what gets encrypted there. So this is another level of attack. Why is this more capabilities than just the ciphertext? Yeah.
You know what to compare the fragment?
Yeah.
Compare to when you try to use the
Yeah, because if you only have ciphertext only, you didn't choose. You don't know what the underlying message is. But if you get to choose, you maybe get to manipulate things in a way to be good for you. I guess I lied. Sorry. You're incorrect. Or our example is incorrect. The third capability is to choose the plaintext. The second one is the known plaintext. So I know what the message is, but I'm trying to break the key. Why is breaking the key useful? Because it seems counterintuitive. If I already know what the plaintext is, and I have the ciphertext of that, then why do I care about deriving the key? Yeah, later or previously sent messages, right? Any message that was sent with that key, I could break that. I believe, I need to read up on my history, but I believe like the Enigma machines that the Germans used in World War II were changed like every day or so. So when they were able to break it, they could break an entire day's worth of communication, which was super valuable. Exactly. So a known plaintext attack, right? They knew what that was, and that would give them enough stuff to try to look and break for stuff. Yeah, crazy. Okay, so the other thing to think about is how to approach attacking some of these things. This is the one thing, the beautiful thing that you have is you know that all the assignments that we give you are doable, right? All of these things of breaking these systems, they can be done. So you can use that as a great motivating thing of like, even if I can't do it, I know that it can be done. But the other thing to do is to think about how to approach attacking these things. Sometimes there'll be mathematical attacks. So like the underlying math is bad. I think that's probably what you could say about the Caesar cipher, right? I think in crypto terms, we'd probably say that the key size isn't large enough. The key size is only 25 characters, right? So to do a brute force attack, the adversary would only have to try 25 different things. What if it was, I used an alphabet of 2 billion characters? It'd be harder to brute force, right? Because the shifts would be different. It's a weird example because how would you read a message with a billion characters? But whatever. The point is the shifts. Cool. So if you're a very smart mathematician, you can find flaws by trying to analyze the underlying mathematics of the crypto system. And this is, it could be in how it's set up, how it's configured. There's a lot of like CTF attacks that deal with these kind of problems. I think, Connor can correct me, but I think for most of the ones, the underlying math is actually correct and fine. And that's actually a lot of systems nowadays. They use the underlying cryptography, and it's fine. We'll see other ways to attack them, though. So one of the other classic attacks, and we'll look at this on a Caesar cipher, is statistical attacks. So what do I mean by statistics? Is that just like a terrible... Do you have to take statistics as a CS? Yeah. So see, we force you to take it. It comes up again in here, so you can be like, yes, that was useful. But why? Anybody play Scrabble? Anybody know what Scrabble is? Has ever seen a Scrabble thing before? What about like Wheel of Fortune? Yeah, slightly more. Why are tiles different points in Scrabble?
Because some are harder to put into a word than others.
Why?
Because they're not as common.
Yes, they're not as common. Every letter in the English alphabet is not as common. Similar on Wheel of Fortune, when you have a puzzle you need to guess. Do you guess Z first? Hangman? Two people played Hangman, right? Something? Right? You're guessing what a word is based on letters. Why do you not guess Z first? It's uncommon. It's highly unlikely for all possible words that word exists in here. So if we make some assumptions about what the underlying language is, let's say it's a German message, we'd say they're probably speaking German. If it's an English person speaking, we'd probably say it's probably an English message. And so we would try to examine the ciphertext and correlate properties with our assumptions. So try to see, okay, this is actually a way, depending on the ciphertext, of how you can tell. We'll look at this with breaking the Caesar cipher, but you can break the Caesar cipher without doing brute force, just by doing statistical analysis. And you shockingly don't need that many words in order to have this be effective. Okay, but let's say you're using a good modern crypto system. These two things are impossible. Do you go home? What else is left? A wrench? I guess I should have that XKCD comic ready. You just beat them up until they tell you the secret key. It's possible, but you social engineer, that could be one. But we kind of care more about the computers in this context. Let's not beat up the computers or try to social engineer the computer. So what else is left? Everything's perfect? All the software you write is perfect? None of you have ever written buggy software? Do you think the people that write cryptographic software is similar to you or different? They're perfect? They're gods that walk among us who write perfect code? No, they're not. They're not different than you. They're the same. Hopefully slightly better, because maybe you will get better too. That's the point. It's not about where you are now. It's about where you will be. So the other key thing is implementation attacks. So bugs in the implementation. There's sometimes some implementations maybe will let you specify the key. So you give a key of like a Caesar cipher of 0 and it just uses that. And then now it has no encryption. There's been all kinds of crazy bugs in this stuff. So this is another thing that happens a lot, is that implementation introduces a flaw. I think I mentioned this before, but also there's timing attacks that they can do. So if I give you different crypto operations, but based on what data I give you and based on what the key is, causes different timings to occur, I can actually use that to derive your your secret key. It's absolutely crazy. And they've taken these attacks even further to where they could listen to the sound that your computer makes. Anybody have like a computer that makes sound that's like crunching data and stuff? Yeah, when it gets like hot, like they've even done it of like, they put a wall monitor to monitor the power draw on like a server, and they can tell based on the power draw and extract the secret keys from the computer. Just all kinds of crazy stuff. Okay, so what we looked at before, the Caesar cipher that we looked at is an example of what we'll call classical cryptography. The other name for this is symmetric cryptography, because there's a very important point that we didn't talk about. In our Caesar cipher, if you and I are exchanging messages, how do we both know K? We got to tell each other. It's not magic. We have to tell each other. If we could tell it to each other, couldn't we just share that message? Right? So a key notion here is that the sender and receiver have some out of band way, some secure way to transmit the key to each other. Otherwise, the adversary can just watch us when I say, the key is 4, and then you go over there and they go, great, all these messages, the key is 4, and then they'll extract them. But what's shocking is the Caesar cipher that we used. So this is a type of cipher called the substitution cipher, where you substitute one, let's say in this case, character for another. So we substitute A for D depending on the key. This is one type. The other type is transpositions, moving things around. And what's crazy to me is like modern symmetric crypto systems are all based on this. Just combinations of swapping things around and moving things around. They just do it a lot in ways that's hard to go backwards, but easy to go forward. Cool. Okay, so we looked at this, the Caesar cipher. So we can encrypt, so the key 3, then we can encrypt hello world to KHOORZRUOG. Right? And it's kind of, if you think about back in the day, this actually like does look kind of crazy because, I don't know, that's like a random gibberish word. Okay, but if we're attacking this, like we said, we can just try all possible keys. But the interesting thing is doing the statistical analysis. So what we do is compare this to so 1 gram, meaning like 1 character model of English. Like how likely is this character to appear? You can actually use 2 or 3. of how likely is this character to follow this character. When would a 2-gram be useful for what letters or what things? Like what letter usually always follows another letter? English? You speak English? U with what? Q? QU, right? After a Q, it's highly likely that there's a Q. So if you knew that there was a Q in one spot, you'd be able to say confidently that there's a U in the next character. Yeah, so these are all the things you can use. You can actually just go look this up. There's like Wikipedia English, distribution of languages of English. Here, we can look at it here. This is from Wikipedia. This is the letter frequency for each one. So our intuition that Z is highly unused is definitely correct. What stands out is like E, T. So what we can do is, if we have some ciphertext that we know is encrypted with a Caesar cipher, so this is an example of a fixed ciphertext attack. We're trying to derive the secret message and the key. So we can actually compute the frequency of each letter in this ciphertext. So this is probability, or this is a frequency. So the most common is B, H. I think that's correct. And maybe E in here, right? We compare that here, and then we'd say, okay, so one thing we can do is calculate the likelihood of each key. So we can actually calculate, I'm not going to get into this math because it's not super important. We can calculate how close, using statistics, how close, if we shifted it by 1, 2, or 3, are we to this graph? And we can calculate this. So we can see a shift. This means a shift of 23 is 0.5. And we can see what's most likely. Oh, this is in descending order of most likely. I was wondering why it was going like that. That's very weird. So we could try now, rather than trying brute force, we can try a ordered list and say, okay, let's try 23, 13, and 7. So we tried 23. We get something like this. Does that look correct? Nah. We can try 13, although Phobaliz, it almost looks like it could be right, except for like BYGX. That seems like not something I've ever heard of. 13, you should never build your own crypto. 7, blah, blah. Kind of crazy, huh? So you can build these systems up. You can make them more complicated. You can have a, rather than having one letter key, you can have a multi-letter key. So you do shifts for each character in the key. But we're going to skip all that. They'll be in the slides if you really want to like dig into this stuff. So in the real world, when do we get out? 2:45, right? Good. Oh, cool. We're like right on time. Look at you guys. All right. In the real world, rather than using shifts, which are easier to conceptualize and just think about normally, we use XOR instead of shifts. Why is that? Yeah. Shifts, well, I'd say they're both equally easy to shift. It just kind of depends on what you're doing. So it's more, honestly, the computers are very good at XOR and less good at shifts. They need to, like, the mod operation requires some math. XORs is very easy. You can do that physically in hardware, and it's very, 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 very fast. Also, it's what's the word I'm looking for? Commutative. Anybody do math? So A XOR B is equal to B XOR A. And if you get A XOR B equals C, C XOR B equals A. So for all of these examples, like in class and stuff, we're going to be using XORs instead of shifts. Shifts is easy to get the concept of. Cool. Also in the real world, the things that happen is everyone thinks like, I'm smarter. I've taken a cryptography class. I've read things on the internet. I will create my own crypto system. You should not do that. Like, if anything this teaches you, do not do this. It is so easy to mess up. As you'll see in the module challenges, you're actually going to be like attacking crypto systems that use something like AES that is cryptographically secure. It's just used in a slight way that allows you to completely break the whole thing. So it's incredibly easy to mess up. So one of the key takeaways of this is don't do it. Use a good library. If you have questions, ask somebody or ask me, I guess. But I don't know. It's a weird question to get. It's, I guess, 3 years after you take this class. Like I said, there's side channel attacks. So there's crazy attacks that can happen. And when I say side channel, this would be there's attacks that use the cache on the CPU. So we looked at the chip of the CPU, right? Way back in the day when we were talking about assembly. When data is pulled from memory, other data gets pulled in. It turns out for some cryptographic algorithms, what data gets pulled in tells you something about the key. And so there have been attacks where people can figure out what from one process, what another process the cache is using, because the caches are shared amongst processes usually. And it's able to probe and figure that out in a crazy way so that they can infer what the key is. We've done some research stuff on this. It's nuts. Like I mentioned, timing attacks. It's so easy to make subtle bad changes that really mess everything up. What if you're on a panel to develop a newer version of something like AES? If you do that, you are an actual cryptographer. So obviously, if you become a cryptographer and do research in this area, then this does not apply to you. If that's your job is making crypto systems, then good for you. But I'm very confident to say that most of you will not be doing that, and that is fine. But as you'll see, cryptography comes up so much. You'll have challenges in your programming and development careers where you're like, oh yeah, I want to store some data, or I'm storing user data. I should encrypt that so that way people can't read it. And then you develop some mechanism that's absolutely garbage and messes everything up. Cool. So we're going to go over the history of these things, and then I'm going to demo some stuff because there's some stuff I want to show you. So anyways, the history of modern symmetric encryption. So this idea that we have this key, we've somehow shared it, and I'm going to get some data and send it and encrypt it, is a very active area. We'll look at very slightly some of the history here. So you want something that's fast. Well, why do you want it fast? Shouldn't you want it to be slow? If it's fast, then adversaries can be fast, right? And if the encryption and decryption is fast, then it's easy for an attacker to brute force things. So if it's slow, then it'll slow them down when they're brute forcing. Seems great, right? What's the problem? What?
Your data retrieval also very slow.
Yeah, makes your data retrieval slow, makes your program slow. And guess what? If you as a developer have a choice between something slow and secure or fast and insecure, 9 out of 10 times people choose the fast and insecure. If you had a choice between fast, insecure, and fast, secure, you should choose fast, secure. It puts up barriers to adoption. Anyways, so the history that I will go over starts at DES, which is the Data Encryption Standard. This was proposed by IBM for encrypting sensitive, unclassified government information. It was standardized in 76, 77. After tweaks from the submission, after consultation with the NSA, this is like fascinating. So they were proposing the standard. They kind of sent the design to the people at the NSA, and they said, well, switch these things around, and then sent it back. So what do you think they were doing? Trying to figure out how it works and doing what? Why would they propose changes?
Because they did figure out how it works.
And what? Did they make it better or worse?
Like security holes in it, I guess, or like
Yeah,
it's
so
not
one
quite as secure as it could have been.
So one case would be they fixed a bug in it, right? Made it more secure. What's the flip side? Made it less secure, right? Put in something that they could break and only they could break and nobody else could break. How are you to know if you're IBM? You've already analyzed this. You thought this thing was great. And then you see changes and you think that's great too. So we'll get back to that. This operated on 64-bit block size. So the blocks of data that it encrypted were 64 bits and it had a 56-bit key. So this is like, again, don't take notes on the details of this algorithm. I do not care if you memorize or understand the details here. What's important is understanding what's going on and all of this data mixing that's going on here. So you first have the plain text comes in. There is this IP phase, which is initial permutation. So all the bits from the plain text get mixed around. And then those bits get fed into this F function, which then gets XOR'd with the, I think this splits in half. So the back half goes in and the other half comes out. And then it gets passed this way through F, XOR'd for 16 different rounds of this. And there's a final permutation. And then finally you get the 64 bits of ciphertext as output. This F, yeah. So this PC1 was this crazy permutation. Oh, this is the key that comes in. So the key comes in and then it's like permuted in this way using that thing. So like, this just means like this bit over here goes over here and this bit here goes over here. That gets mixed around and then these left arrows are left bit shifts. So the bits get moved around and then shifted around, and then some of that 48 bits goes into here and 48 bits goes into here. This PC2 is a different shift. Then digging in more, each of these, like this half block of 32 bits that we saw, gets passed into an E function, which then gets XOR'd with those 48 bits that were coming out of the key. Those then get passed into these S boxes, which is a substitution box. So each of these S1 through S8 is a table that says if the input is these bits, output these bits. So it's a substitution cipher, just like the Caesar cipher. Yeah, so this is the E function that does this like weird mixing and extending thing. And then this final P, this P here, this permutation is another permutation thing. Everyone good? Good for the test on this? Just kidding, that was a joke. Won't be a test on this. And these were what I said, the S boxes. So each of the S boxes has different substitutions to say, okay, if it looks like this on this side and this on this side, then the output is this. Absolutely insane. And it was one of these things that was changed. So literally the NSA suggested, I don't remember exactly where, of like change these parameters here to these other parameters in this table. And so one of the key problems, actually why DES is no longer around, is first the key size was too small. So we looked at it for, there's 56 bits. So that means your keys to try are 2 to the 56, which looks like a large number, right? If I gave you this many dollars, you'd be probably pretty happy. No? I think some of you are like, no, I want more. Even if I gave you that many cents, that'd probably be pretty good. I don't have that money to give you, just to be clear. This is a hypothetical. But remember, this was developed in 1975, 76. How fast were computers then compared to that computer in your pocket right now? Like not anywhere close, like absurdly, like just, I don't know, it's hard to overstate how absurdly fast things are now. And you can build custom hardware to brute force that. So in 1998, the EFF built a custom thing that could crack DES keys for 250,000, and it could break a key in 2 days. You think that's impressive? Further along, in 2009, a machine built out of for $10,000 was able to crack it. Was able to crack DES keys. So this is how like you can see that cryptography changes over time. Now, what's absurd, going back and finishing the story about these magic NSA changes, it turns out that this notion, there's an area of differential cryptanalysis, of attacking these systems, which was discovered in the late 1980s. So this was proposed mid 1970s. It wasn't until the 1980s that this concept was discovered by public academia, and it was identified that the prior version was vulnerable, but the new version was not. So it turns out that, so what does this then tell you about what the NSA knew in 1976?
That it was already vulnerable?
The prior DES version was already vulnerable. What does that tell you about what the NSA knew? Say it again? They knew how to do this like 10 years, a decade before the public knew how to do this. And that they actually did fix it. So if you were thinking they injected a bug, at least to our knowledge for DES, they did not inject a backdoor into that standard. And then there was new attacks in 1993 of linear cryptanalysis. So it was finally withdrawn as a standard. And so now the standard is AES, the Advanced Encryption Standard. This is where somebody was mentioning being on a panel. So I believe this was the government created a competition to create the next crypto system to supplant DES. And there were several different standards. They were all evaluated. It was like an open competition of proposing attacks, all this kind of stuff. But it was standardized in 2001. So after a 5-year process of evaluation and everything, it operates on 128-bit blocks. Keys can be either 128, 192, or 256-bit. And yeah, so it's actually... anyways, you can use it to encrypt secret or top secret information, which is pretty cool. And Intel, again, in the name of making things faster, extended the x86 architecture so you can use assembly instructions to do AES operations on the chip and do it much faster than in software, which is pretty cool. Okay, I am missing slides. Why am I missing slides? Dun, dun. Where is my pad? I think I hid a slide I was not supposed to hide. All right, let's look. Otherwise, I'll just skip over to Connor's slides. All right, I'm going crazy. Okay, we didn't talk about, which I want to talk about, the most secure crypto system. So believe it or not, there is a provably secure, you can never break it crypto system. It's actually incredibly simple. You could do this. The idea is if you have a key that is randomly generated, that is the same length as the message, I take the key, I XOR it with the message, and then I send you the ciphertext. Why can't you break that? Yeah. It's impossible to do statistical analysis. The key is, as long as the message, it's 100% random, which means you have no way of knowing, getting the ciphertext, what that original key is. It could have been, if you think of each bit as a 1, like the ciphertext is a 1 or a 0, the key could have been, has equal probability, each bit of being a 1 or a 0. Therefore, if you tried to brute force, it's the exact size of the message. You'd have to try every possible bit combination of your message. Now, what's the problem with that?
Modern computers are so fast you can potentially brute force it anyway.
No, modern computers are not that fast because I can send a long message that is 1,000 bits, and you'd be brute forcing 10 to the 1,000. Yeah.
And if you get 2 keys, you can compare the ciphertext.
Yeah. So if I reuse the key, right, and I say, okay, I send you message A with the key, and then I send somebody else message B with the key. Because it's XOR, you can just take message A and message B, XOR them together to get the key. So that's why it's called a one-time pad, which means I use the key for this message and then never use that key ever again. When I want to send a new message, I have to generate a new random key. Now, what's the problem there? Yeah.
I'm just going to ask a question. Is that what your logo actually
No, nothing uses this, and here's why. Because, yeah, go ahead.
You can't safely deliver the key.
How do I deliver the key? So the key has to be random as long as the message, and I can never reuse it. So one thing to think about is why wouldn't I just, if I had a secret way to send you this key, why wouldn't I just send you that key? Or send you the message, right? Rather than securely sending you the key, here's the message. Now, maybe we arranged something beforehand, and this was actually what the military used code books. So they would have just a book of random letters, and they would exchange these books. And then when they wanted to send a message, they'd start at the start, use those things, rip up that page, send the ciphertext, and the next time they wanted to send the message, use the next page, send the message, rip it up, next page, and so on. So they would never reuse it. But the problem is sending lots of data is insane because you have to have that amount of secret random data shared between two parties. This allegedly Yeah. So I don't know if it's. I should actually look up if this is used anywhere now. I don't think so.
You have a random stream. Like the idea is there.
Yeah, but like this notion of like actually pre-sharing this random key between two parties. But if you can guarantee it, then you can actually guarantee perfect secrecy. Yeah, this is the XOR, fancy XOR thing. So here we can look at an example. This is a bad key, bad key, not random key, bad key. But we can take the plain text hello world, XOR each byte with the key byte, and because it's the same length, we would get some ciphertext. And if you didn't know that this key was a non-ASCII string and was random, you would actually never be able this is like perfect 100% security. It's impossible to reverse engineer or to break it. Sorry. And to decrypt it, we just do the reverse, and it's incredibly easy. Okay, I want to do that because I want to go over and demo some of the assignment. I haven't set it up. We'll set it up later so that it's in your thing. Okay. For these ones, actually what do you guys want? SSH, desktop, or I don't even know if I want to offer VS Code. What? Desktop? Okay. Okay, so let's get in here. Challenge, run. Welcome to Cryptography. Thank you, challenge. In this series of challenges, you'll be working with various cryptographic mechanisms. In this challenge, you'll decrypt a secret provided with a one-time pad. Although simple, this is the most secure encryption mechanism if you could just securely transfer the key. Hey, that's just what we said. That's good. Okay, so this is the key. It looks something like this. Here's the ciphertext. It looks something like this. Why does this look like gibberish? Yeah, it's encoded using the B64 is the hint here. Actually, maybe I don't want to do that one. You can do that one. This is base 64 encoded, so this is a nice way of sending you data that could be binary, random, like a null byte, or because after you encrypt something, it could have literally random gibberish in it, right? So it's not always ASCII. So this is sent to you in base 64 encoding. So we can use if we wanted to, let's look at this secret ciphertext, base 64. We can, of course, use our favorite man, look at it, encode, decode data, print to standard output, base 64-D. Now anything I paste in will be, hello, stop that. Okay, so paste this in, paste it in, paste it in. Third time's the charm. Paste it in. Enter, Control D. I get a bunch of gibberish. So I can see what that gibberish looks like by using hefstump-C, which I talked about sometime in the past. So we can see that these are the bytes that this decodes to. AE 47, EB, FC 9E, 0F, EC, but man, that's like really painful to type in and deal with. Plus, if we needed to interact with this several times, if we have a chosen plaintext attack where we get it to encrypt things, we may want to interact with it. So let's open up Emacs. What's this? Crypto 2? Crypto. Okay. Okay. All right. So okay. The one thing I will say, I've been almost all the stuff that we've been doing up till now, you don't need to use Pwn tools to do, but it's helpful, and so we've been pointing you towards some resources. Interacting with programs like this is way helpful to use Pwn tools. It has a lot of really cool built-in mechanisms to interact with another process. And I will say, how do you all think about the documentation of Scapy? Yeah, you may say, what documentation, right? That's kind of the joke. Yeah, the documentation is terrible, but Still, Scapia is one of the best tools for what it does. So that's why you have to use it, because it's very good, or you don't have to, but that's why it's very good for what it does. Okay. We can, so P, I will say so that, that Pwn Tools has excellent documentation. This is part of the reason why it's so useful. It just has fantastic documentation. You can look at like any function you're using. Like I'm going to use process to execute a process and interact with it. Yeah, it's got so much cool stuff that you can really like just learn a lot in here. So I'm going to do process. So what this is telling Pwn Tools is, hey, execute this program, and I'm going to use this process P to interact with it. So I can actually send data to it as if it was coming from standard input from my typing things in. I can read from it, which is what I'm going to do it, because what I'm going to try to do here is extract out this key in this ciphertext, because I need to do XOR operations on them. These are in base 64 encoding. I could do it by hand, by doing this by hand, translating this to bytes, do the same thing for the key, XOR them. But again, you're computer people. You should not be doing things by hand that a computer can do better, faster, stronger. Okay, so I can do P read until I want to write up against here. So there's cool functions, read until. That does exactly what it sounds like. Reads up the standard input up until it gets to that point. Do you need me to increase the font size? Good news, don't know how. Oh, there we go. That's the opposite of what I wanted. Enhance, enhance. Cool, okay. So read until there. And every time you call one of these read until or read line, it returns you what it read up until there. So if I wanted to get something from there, I do that. I don't need to do that. And I'll say key B64 is equal to P dot read line. So this will read until the end of the line. I think I'm just remembering all this stuff, but all this stuff is in there. We can look at what the exact syntax is in a second. Why am I calling this key underscore B64? Why don't I just call it key? Because it's base 64 encoded, and this will remind me as I'm coding, later when I read this program and I have absolutely no idea what it does, that, hey, it's actually base 64 encoded before I use it. So if I try to decrypt something using this key that I just read, that's bad. So I could say key is equal to, I need to import base 64. 64, there's a handy dandy built into Python, base 64.b 64 decode. Okay, let's make sure this worked. Key 64. Man, after that whole rant about how this is useful, I mess it up. Okay. Yeah, there we go. So this was base 64 key. There's my key. There's my bytes. The B is telling me it's a byte string. Now what's the next thing I want to read in? The secret ciphertext, so I can read up until here. Cipher. Oops. P dot read until. P dot read line. Cipher. Boom. The other thing you can do with Pwn Tools, I think, can you do that here? So it's actually insane. I just learned this, I think, this summer. If you just had debugged as like capital letters as one of the arguments, or I think you can even do it as one of the arguments here. No, you can't do that, so don't do that. But Pwn tools will, so see all this debug output? It's showing you the input output of the process as it's interacting with it. So it's telling you that it received hex 138 bytes. These are all the bytes it received. It received this. If I want to send any bytes, it will send bytes back and it'll show me what I'm sending and receiving so I can verify that those are what I think they are. Pretty cool. So now I have my key and I have my ciphertext in bytes. I can do all kinds of stuff. So for I in range length of cipher. So I can do something like print, use a format string and say hex. No, what do I want to do? Hext cipher I. And then hex cipher key I. So I'm just iterating through the cipher and the key, just printing them out in hex, just seeing each of the individual bytes. And now I can obviously very easily write code to do the XOR and print out that, get it into a string, whatever, and now I can get the flag. So this is how you can use this to interact with these programs. Because sometimes you may need to make multiple interactions with a process. And so you can use this in Python to do this rather than doing it by hand. Because if you do it by hand, you have to base 64 encode things as you send things in. It just gets to be a nightmare. But you have code and libraries and cool stuff to do it for you. Questions before I sign off? Yes. Good question. You'll find out tonight. A day? 2 days? A week? Week and a half? I'll just keep going, increasing until I see less panic. A month? No. We got other stuff to do. All right. Thanks, everyone.